back from the break. I am delighted to introduce our next speaker, Larry Zitnick. Larry got his PhD at CMU, and after that he went to Microsoft Research, where he already established an excellent track record in object recognition and other parts of computer vision. And he was happy to be at Microsoft, but eventually Facebook made him an offer that made him happier. And now he's at Facebook. And again, he's doing world-class research. He's the leader of a very influential project called COCO, which is Common Objects in Context. And he also works at the intersection of images and language, which is an exciting area involving things like visual question answering. So thank you, Larry, for joining us today.
Thank you. All right, great. So at Facebook AI Research, what we try to do is we want to advance the state-of-the-art in AI in collaboration with the rest of the community. But given that my background is in computer vision, I find myself thinking a lot, what is the role of computer vision in AI? And that's what I want to talk about today. So imagine that you could go back to 1984, and you could find yourself a graduate student, and you said, here, read this paper. It's got a really cool title. It's called Neocognitron. And if you want to solve recognition, all you need to do is 3 things. You need to figure out how to learn weights, you need to collect a huge amount of data, and you need to find a really fast computer. And you would solve recognition. Now, graduate students being graduate students, they would go in and they'd look at the weights part, and they'd look at algorithms and say, I would want to solve the algorithm. And that's exactly what they did. They went and solved the algorithm. They developed backprop. Now, graduate students being graduate students, then you say, OK, now all we have to do is collect more data. That took a lot longer, unfortunately. So that took probably another 30 years to finally collect enough data to then do the learning. And then as we saw, I think Nicholas was earlier, you can actually get graduate students to create huge compute clusters as well. So that worked out pretty well. But now we're in 2016, and we find ourselves asking the question, how are we going to solve AI? So which direction do we need to go in to solve AI? Well, the answer is obvious. All we need is more data, more compute, and apply backprop. And this is exactly what we've done the last few years. So we took a problem which is seemingly AI complete, image captioning, and we basically took tons of data, tons of compute, and we ran it on these images, and we got some really amazing results. So you look at this, a man riding a wave on a surfboard in the water. Just nailed it. Great image, great caption. A giraffe standing in the grass next to a tree. Again, fantastic caption with this image. And I think a lot of people were really excited about this. But then after a little bit of introspection, we began to realize this doesn't work if you don't have similar images in the data set. If the images are too unique, suddenly the algorithm starts falling apart. So how many people have read this paper, Building Machines That Learn and Think Like People? This is a paper from NYU, MIT, and Boston, or MIT and Harvard. And it's a great read. If you haven't read it yet, please read it. But they took the state-of-the-art image caption generator, they ran these images through it, and they got like a man riding a motorcycle on the beach. Yeah, kind of correct, but kind of missed the point, altogether. And you see this over and over again. If the data sample, the test image is from the head, you nail it. If it's from the tail, it's a little bit unique, completely falls apart. More data is not the solution. So then as computer vision people, you might think to yourself, OK, we want to solve AI. Which direction should we push in? Let's just make our recognition problems harder. So what's something really hard that we can try to recognize? Mirrors. So you have a mirror like in this image here. We'd nail it. We can do a really good job, right? What about this image? Can you detect the mirror in this image? In order to do this, you have to have a much more deep understanding about the world. You need to understand how selfies are actually taken. Some of the older people here might not get it. So, but unfortunately, finding really difficult images like this is really hard. It's already hard enough to create data sets, so I don't think this is the right direction either. So, if we want to solve AI, which direction should we go in? And that's what I want to talk about. There's 2 things that we need to do. The first thing is learning. So there's many different types of learning. There's the very friendly, nice type of learning, which is supervised, where you get data, it's complete, it doesn't have any noise in it, it's fantastic. It's our favorite friend. You have semi-supervised learning, which is a little lazy, let's say, where you don't always get the data that you want. You have reinforcement learning, which is always trying to give you money or give you rewards for doing the right thing. And then you have unsupervised learning, which is really, really annoying. Because unsupervised learning is just a huge amount of it. We have a huge amount of data, but we don't have any labels for it. So, supervised learning. This is our bread and butter. This is why we've had the advances that we've had so far. It's because of huge supervised data sets like ImageNet and more recently COCO. But creating these data sets is incredibly difficult and frustrating. Just ask anybody here who's tried to do this. Ask the graduate students. It's really hard to get graduate students to work on problems like this. Semi-supervised learning. Now let me give you an example of semi-supervised learning and why this is tough. So if you want to learn a concept such as yellow, and you have a bunch of image captions like these, you can have images which have yellow in them, in which a caption actually mentions yellow, but then you have other captions like this one here, in which then the entire image is yellow, yet it doesn't actually mention the fact that there's any yellow in the image. Now you can learn really cool things using data like this. You can learn whether people actually say whether a certain visual concept is present in an image or not. So we can learn a classifier which says, hey, when there's a fence in the background of a soccer game, nobody ever mentions a fence. Whereas if there's a fence which is blocking the bear from eating you, somebody's going to be mentioning that fence. Reinforcement learning. Now, reinforcement learning, computer vision, is kind of a weird mismatch right now, because in reinforcement learning, generally you have some sort of interactive environment. And it's hard to do that with the static data sets that we're used to. So what you'll find is a lot of the reinforcement learning right now is being done with gaming type interfaces or interactive sort of interfaces like this. And I think it's still a really exciting area to be looking into. And then we have unsupervised learning. And this is kind of the elephant in the room. Because there's a huge amount of data. If we could figure out a way to learn features using this unsupervised data, we could do amazing things. So people have been trying to propose all sorts of different kind of tasks that they can do learning from, such as, given these 3 video frames, are they in the correct order or not? And you see what type of visual features they can learn from doing these sort of tasks. Works kind of okay, but still not as good as supervision. So the next thing I want to talk about is reasoning, and specifically visual reasoning. And here, I don't actually want to talk about the task of reasoning itself. What I want to give you is a sense for how difficult this problem is and where we are as a community in solving reasoning. So very recently, there's a paper that proposed the following task. You're given 3 statements. Mary went into the hallway. John moved to the bathroom. Mary traveled to the kitchen. And you have to answer a very simple question. Where is Mary? Computers have a really hard time of answering that question. Just let that sink in. This is trivial, really trivial, yet we cannot do it because we can't understand what these statements are actually saying. And people are worried about AI taking over the world. If you're going to do reasoning, you need to be able to predict the world. You need to be able to see how things are going to progress into the future. Where are we right now? Right now, when we think about prediction, we're dealing with these sort of baby tasks where we have, like for instance here, we have a bunch of blocks. They're stacked up on top of each other. All you have to do is predict, are those blocks going to fall over or not? It's incredibly simple. And if they do fall over, maybe which way are they going to fall? This is something that can be done by a baby. Yet this is the state of the art in the research right now. And you think about more complex prediction tasks where we have to model human behavior, where we have to model, simulate driving down roads and that sort of thing. We still have a long way to go. Data. This is something that's interesting because when you think about these AI tasks that we're currently looking at, a lot of them are dealing at a higher level reasoning. They're not looking at pixel level things. It doesn't matter if you start with real data or if you start with more abstract data. So there's been a lot more work in looking at abstract scenes, cartoon scenes, looking at Atari games, looking at Minecraft. These other areas where we can then kind of isolate the reasoning problem that we want to explore without having to worry about this messiness that is the recognition problem in the real world. And finally, even if we solved reasoning, how would we know that we solved it? We all know the problems with the Turing test and how incredibly frustrating it is to measure intelligence based upon the Turing test because there's all sorts of different ways of gaming it. And one of the more recent things that we proposed is to use visual question answering as a sort of Turing test for reasoning and vision. So what you do is you have an image, you have a question, and what's nice about it is it combines the visual recognition that now is beginning to work better along with the with the reasoning that we want to explore. And if you can do both of them well, then you can do good on the VQA task. And so far, what we've seen is that progress in this task hasn't been moving that quickly. And I think a lot of it is due to the fact that reasoning is not progressing that quickly, unlike recognition. So looking forward. So up until now, up until 2016, we've made incredible strides in recognition. I said before that recognition is solved, but recognition's not really solved. There's a lot more work to be done. But compared to 1984, it's essentially solved. Now, if we actually want to solve AI, we need to turn. We can't just keep pushing on recognition. We can't keep thinking of AI as recognition. We need to start thinking about AI as AI and start solving these problems that have been around, that have been kind of ignored over the last 30 years. And if you look at reasoning in particular, we're just at the beginning stages of this. And for me, this is what's so exciting. There's still so much work to be done. And high level, what's interesting is that it's not a clear roadmap. We don't know how reasoning is going to be solved. We don't know how learning is going to be solved. We don't know how we're going to crack the unsupervised learning problem. Because of this, it's hard to give a time frame. But one thing I can guarantee is that as we explore AI, is that computer vision is going to be our playground for research in this area. Thank you.